Right, so today we are going to be looking at the first lesson of our stereochemistry topic, which is our new booklet. So I will pop a copy of this booklet into the Google Classroom in case anybody needs to access one. If you've lost yours and you want to print it out or whatever, then I will pop that there for you. So just starting with our little cover page. Now this cover page, unlike a lot of the cover pages for the organic topics, is actually very educational and very useful. It does actually show you quite a lot about what we are going to be doing in the stereochemistry topic. So basically stereochemistry is all to do with isomers, and unlike what we kind of know up to this point, there are actually lots of different types of isomers. So let's begin. So for stereochemistry, it's the branch of chemistry that's concerned with the three-dimensional arrangements of atoms and molecules and the effect of this on chemical reactions. Typically, molecules that have the same molecular formula but different structural formulas are known as isomers. Isomers are distinct molecules which can have very different chemical and physical properties to each other. There are two ways in which atoms can be arranged differently in isomers. We can have structural isomers, which is the isomers that we know up to this point, and we can have stereoisomers. So let's just start with a little recap on structural isomers. So in structural isomers, the molecules differ in terms of the order in which the atoms are joined together. For example, the diagrams below show a number of different structural isomers with the molecular formula C3H8O. So let's have a wee look at some possible isomers with this particular structure. So we could start by popping the 3 carbon atoms in a line, popping an OH group on the end, and then having the rest of our hydrogens surrounding the carbon. So when we count the number of carbons, hydrogens and oxygens, you'll see that that does match the molecular formula of C3H8O. Now looking at this particular molecule here, we can see that it has a hydroxyl group, which means it is an alcohol, and that hydroxyl group is on carbon number 1, so that would be called propan-1-ol if we were naming it. Okay, so let's look at a different way in which we could arrange those 3 carbons, 8 hydrogens and oxygen. So let's have a look at keeping those 3 carbons in a line. And then this time, let's think about popping that OH group onto a middle carbon. Popping the hydrogens around our carbon. And that would be an isomer. Now, this particular arrangement would be known as propan-2-ol, because the hydroxyl group would be on the second carbon. Now there is one other isomer that I can think of for C3H8O, and this would look like this one. So rather than popping all of the carbons in a row, I'm going to pop an oxygen in the middle of the carbon chain, and then pop my hydrogens around the carbons so that each carbon is making 4 bonds. Key thing here is to make sure that you are following your rules of bonding. So carbon should be making 4 bonds, oxygen should be making 2, and hydrogen should be making 1. And you can see that that is another way of arranging 3 carbons, 8 hydrogens and 1 oxygen to get another isomer. Now this particular structure that I've drawn is a example of something known as an ether. Now ethers are something that we will be looking at a little bit later in the organic chemistry course, but for just now it's enough for me to just say that it's an ether. And what I will do is I will name it, just so that when you finish the course and you look back, this will all kind of tie together seamlessly. So this particular structure is called methoxyethane. Okay, now, when looking at our three different isomers, our first two, propan-1-ol and propan-2-ol, will have very similar chemical properties. They won't have identical chemical properties, but they will be similar. So you would expect their melting and boiling points to be similar. You would expect their solubility to be similar. But they aren't the same. For example, propan-1-ol and propan-2-ol do have different melting and boiling points. And then when we look at our third isomer, methoxyethane, the properties of methoxyethane are vastly different to propan-1-ol and propan-2-ol. For starters, methoxyethane is not soluble in water, whereas propan-1-ol and propan-2-ol are soluble in water. The melting and boiling points of methoxyethane are going to be much lower than the melting and boiling points of propan-1-ol and propan-2-ol. So it is okay for isomers to have very different chemical and physical properties. Another example is that propan-1-ol and propan-2-ol could undergo oxidation reactions, whereas methoxyethane could not undergo an oxidation reaction. So that's just like a couple of wee things to note. So let's now move on to stereoisomers. So in stereoisomers, the order of bonding in the atoms is the same, but the arrangement of the atoms in space is different in each isomer. Within the stereoisomers category, there are two different types of stereoisomer. So we've got geometric isomers that we're going to look at in this lesson, and we have optical isomers that we will look at in the next lesson. Okay, so geometric isomerism. So geometric isomerism is a type of stereoisomerism and usually arises due to the lack of free rotation around a double bond. So just going to highlight that there. Now that lack of free rotation around a double bond is usually a carbon-to-carbon double bond. It could be another type of double bond, or it could be a carbon-to-carbon triple bond as well. Any bond that doesn't allow rotation would lead to potentially having geometric isomers. So free rotation is not possible around a double bond, as any rotation of the bond would result in the breaking of the pi bond. So remember, a carbon-to-carbon double bond is one sigma bond and one pi bond. And because the pi bonds are in a sideways overlap, if you try to rotate the bond, you would actually break that sideways overlap. So that's what kind of stops that rotation happening. So we're going to look at an example, and we're going to look at the geometric isomers of butene. So I'm going to start by drawing butene the way that we would usually draw it, and then I am going to redraw butene in a way that makes geometric isomers far easier to see, okay? Because our kind of standard way of drawing the arrangement of atoms around a carbon-to-carbon double bond is absolutely hopeless for looking at geometric isomers. So let's begin. So if we were drawing our butene, I'm quite sure we would all come up with something that looks like that. So what I'm going to do is I am going to redraw this, and I'm going to show you the absolute key to the redraw of this. And it's all around how we arrange the atoms around the carbon-to-carbon double bond. So this carbon-to-carbon double bond is key. So I'm going to just start with that carbon-to-carbon double bond there. Now, we should have the atoms bonding from that carbon-to-carbon double bond at a 120 degree angle from each other. So basically, that's 120 degrees, that's 120 degrees, and that's 120 degrees. So that's the way that should be drawn. Obviously, it's not going to be perfect and precise, but that's absolutely fine. But basically what we don't want is we don't want what we see over here, which is the bond coming off of the carbon with the carbon-to-carbon double bond kind of straight across from it. Right, so what I'm going to do now is I'm going to draw all of my other atoms in. So I'm focusing on that carbon-to-carbon double bond. So looking at the carbon on the left-hand side of the carbon-to-carbon double bond, which is a bit of highlighted in blue, we've got a hydrogen attached to it. And we've also got a carbon with 3 hydrogens. So I'm just going to shorten that to CH3 just to make things a wee bit easier. Notice how I'm writing that as H3C so that the bond is going between the carbons, because the bond's not going to go from the carbon of the carbon-to-carbon double bond to one of the hydrogens. So it is important that you do kind of bear that in mind. And then if we look at the right-hand side carbon of the carbon-to-carbon double bond, we've got a hydrogen and we've got a CH3. However, that is not the only possible way that I could have drawn that. So let's look at the other possibility. So I've decided, just based on the way that I've drawn this, to pop both of the hydrogens at the top of that molecule there. However, I could draw it so that one of the hydrogens is on the top and one of the hydrogens is on the bottom. So let me show you what that would look like. So I'm going to start with the carbon on the left-hand side. I'm going to keep that first hydrogen on the top, and then I'm going to pop that CH3 on the bottom. But then when I look at the carbon on the right-hand side, for this one, I'm going to pop the CH3 on the top and the hydrogen on the bottom. And these two molecules that I've drawn here are different. They are isomers, specifically geometric isomers. So when we have both of the non-hydrogen groups on the same side of the double bond, like we do have in this first example here, we refer to that as the cis isomer. So that's CIS. So when we write that, it would be called cis butene. And then the molecule that we've drawn on the right, in which the non-hydrogen groups are on opposite sides of the double bond, that would be known as the trans isomer. So that would be trans butene. So let's just kind of highlight that. So we can see our non-hydrogen groups there are both on the same side of the double bond, the kind of bottom of it. And then with this second one here, the trans isomer, we can see the CH3s are on opposite sides of the double bond. One's on the top and one is on the bottom. So it says, note, it is important to draw the atoms arranged around the double bond as shown above. The atoms attached to each side of the double bond are not linear to the double bond itself. They orientate themselves at a 120 degree angle to the double bond. And what I'm going to do is just pop a wee diagram just in that little bit of space at the kind of side, just to put a wee reminder in for that. So I'm just going to leave the bonds open and we'll pop in our little markers for our 120 degree angles. Okay. Right, the two different geometric isomers are known as cis and trans isomers. In the cis isomer, the non-hydrogen groups attached to the double bond are on the same side of the double bond as each other, and in the trans isomer, the non-hydrogen groups attached to the double bond are on opposite sides. So for our cis isomer, they are on the same side, and in the trans isomer, they are on opposite sides. Okay, now geometric isomers actually have surprisingly different chemical and physical properties. We would maybe expect that the chemical and physical properties would be identical, but they're actually not. So the trans butene has a boiling point of -106 in comparison to the boiling point of cis butene, which is -139. I mean, that's a fair difference in boiling points. And then for the melting points, the trans isomer has a melting point of +4 and the cis isomer has a melting point of +1. And it also appears that having non-hydrogen groups on the same side of the double bond can have advantages in chemical synthesis. It allows cyclic intermediates to form with the cis isomer, which would not have been possible with the trans isomer. So I'm going to put in a wee example here of this. So this isn't something that's going to come up in your exam, it's just something that I want to kind of use to show you the kind of and reinforce the differences between the two. So I'm going to look at the cis isomer first, the one that can form the intermediate, and then we'll look at why that's not possible with the trans isomer. So starting with our cis isomer. So okay, so what we've got is our carbon-to-carbon double bond, and the non-hydrogen groups coming off of the carbon-to-carbon double bond are actually carboxyl groups, C double bond O, OHs. And as you can see that they are both on the same side, which makes this the cis isomer. So what can happen here is we can do a little dehydration reaction, which will involve removing water. Now, because those two functional groups are like right up in each other's faces, because they're like talking to each other, it is possible for a water molecule to be removed from them. So what we would end up with as a product here would be something that looks like this. And we would have a little molecule of water that's removed as well. So this is our little cyclic product. It's cyclic because it is in a ring shape or a circle. Now if we were to look at so I'm just going to label that as the cis isomer. So if we were to look at the trans isomer, we'll see how that's not possible. So I'm going to redraw. So I'm going to pop that C double bond O, OH group up on the top there. And I'll pop our C double bond OH group on the bottom there. Now what you can see is that the functional groups are nowhere near each other. So there is absolutely no way that a hydrogen from one of those carboxyl groups and the OH from another of those hydroxyl groups would be close enough to each other in order to be removed. So for that particular one there is no reaction. Okay, so it's just another wee difference between our cis and our trans isomers. Now, it is important to consider that just because a molecule contains a carbon-to-carbon double bond does not necessarily mean it has two different geometric isomers. Okay, so let's look at some examples where a molecule does have a carbon-to-carbon double bond but does not have two different geometric isomers. So for our first example, we're going to look at propene. So what I'll do is I will draw propene the way that we usually would, and then I'll do the redraw just so that you can see exactly where everything is coming from. Right, so here is the way we would usually draw our propene. I'm then going to do a little redraw and orientate everything in the correct way. So again, what I'm going to do is I'm going to highlight that carbon-to-carbon double bond. In an exam or when you're doing questions, I think that's one of the best things that you can do because it really focuses your attention on the part of the molecule that's important, and it stops you getting distracted, particularly when the molecules get quite busy. So looking at the carbon on the left-hand side, there's two hydrogens attached to it. And then the carbon on the right-hand side of the double bond has a hydrogen and a CH3. So, looking at this particular molecule here, because one of the carbons in the carbon-to-carbon double bond has two of the same group attached, two hydrogens in this case, it doesn't matter which hydrogen points up and which hydrogen points down, it's going to be the same. So there isn't actually a possibility of getting geometric isomers with propene. So it's just propene. So propene has three hydrogens around the double bond, so cannot satisfy the conditions required for a geometric isomer. We need the groups that are attached to the carbon-to-carbon double bond to be at least two different groups. So, looking at our second example of 2,3-dimethylbutene. So I'm going to draw that one again in the usual way. So we've got a methyl group on the third carbon, a methyl group on the second carbon. So that's probably the way most of us would look at drawing 2,3-dimethylbutene. And again, I'm going to redraw, starting by highlighting that carbon-to-carbon double bond, drawing that carbon-to-carbon double bond in. Right, so let's have a wee look. The carbon on the left-hand side of the double bond we've got a CH3, which I'm going to write as H3C to make sure that the bond is between carbon to carbon. And then if we look at this other part of the molecule here, we can also see that that's a CH3 as well. That's just it drawn out in its extended fashion. So it's easier for us to just draw it in its shortened structure. So we're going to write that as H3C as well. Then looking at the carbon on the right-hand side of the double bond, we can see we've got a CH3. And then the other part that's attached to the carbon-to-carbon double bond is also a CH3, again drawn out in its more extended way. So what we can see, looking at this molecule here, is that all of the groups that are attached to the carbon-to-carbon double bond are the same. So it doesn't matter which CH3 points up, which CH3 points down. We cannot exhibit geometric isomerism with this particular substance. So, finally, although geometric isomerism is most common in compounds containing double bonds, it is possible in cycloalkanes as the rotation around the carbon-to-carbon single bond is restricted due to the ring system. So I'm going to attempt to show you a little example of a geometric isomer in a cycloalkane. So I'll draw both the cis and the trans. So what I'm starting with is a cyclopropane ring, and I'm going to pop the atoms that would be attached. So I've drawn this carbon at the back with its two hydrogens, one pointing up and one pointing down. I know this does look a wee bit strange pointing down like that, but it is absolutely fine to draw it that way. And then for the carbon on the right hand side, I'll pop a hydrogen and a bromine. And then with the one on the left hand side, I'm also going to do a hydrogen and a bromine. Now, that would be known as the cis isomer, and specifically that is cis 1,2-dibromo cyclopropane. It's a bit of a mouthful of a name. And I'm going to show you the trans isomer, and then we'll go back and we'll kind of highlight the sort of key part. So again, drawing our cyclopropane. This carbon at the back doesn't really have too much to do with the geometric isomer. Now for the one on the carbon on the right hand side, I'm going to pop the hydrogen and the bromine in exactly the same places, but for the one on the left, I'm going to pop the bromine pointing up and the hydrogen pointing down. And that would be our trans isomer. So that would be trans 1,2-dibromo cyclopropane. Now our key here is the cyclopropane ring. It can't rotate this, and I'm going to highlight this carbon to carbon single bond can't actually rotate because of the other carbon to carbon single bonds holding it in place in the ring system. So if you use your thumb and your kind of first finger and pop them into a triangular shape, so touch both of your thumbs together and touch both of your first fingers together and make a triangular shape without breaking your fingers from each other, try and rotate the triangle. You can see it's impossible to do, and it's just like a good sort of visual cue to actually look at how the rotation is restricted in that ring system. And again, we've got our carbon to carbon single bond in the ring system there. So looking at the groups that are attached, you've got the bromines on the bottom of that carbon to carbon a single bond that's got the restricted rotation, and then in the trans isomer you've got one bromine in the up position and the other in the down position. And then to kind of end off this lesson, in short, for a molecule to have geometric isomers, it usually contains a carbon to carbon double bond with at least two different groups attached to each of the carbon atoms in the double bond. So for a molecule to have geometric isomer, contains a carbon to carbon double bond with at least two different groups attached to each of the carbon atoms of the double bond. Right, so I have posted a little exercise for you to do that is all about geometric isomers. It's exercise 2.3. So if you could go and attempt that exercise, I will then be posting the lesson video for the second part of the stereochemistry topic, which is optical isomers, tomorrow. If you've got any questions or anything wasn't clear or you feel anything needs some further explanation, please do just get in contact with me and I will get back to you and with further explanations.